Hey everyone, welcome back, and today let's solve Leetcode problem 3066 titled Minimum Operations to Exceed Threshold Value Part 2. So at a high level rundown, what this problem is really asking us, basically we're given a zero index integer array nums, and we're also given an integer k, and in one operation we can take the smallest integers from the input array nums and remove them from nums, and then append back a new integer to the input array nums, which would be calculated as the minimum of those two smallest values multiplied by 2 plus the maximum of those two smallest values, and we append that resulting value or integer back into the array. Now our goal is simply to determine the minimum number of such operations that we actually need to make so that all of the elements in our input array are at least greater than or equal to that input integer k, right? That's basically what this problem is really asking us to do, right? And again, very important, we can only apply the described operation if nums contains at least two elements because we work with exactly two elements in each operation, specifically the two smallest ones. Right, so let's go ahead and look at the examples here. In example 1, we have our input array nums to be 2, 11, 10, 1, and 3. And in this case, k is equal to 10. And the reason why, and what k equals 10 really means in the context of this problem and in this example, basically we want all the elements in this input array to be greater than or equal to 10, right? Basically greater than or equal to a, which in this case has an input value of the integer 10. Now in this case, we need only two minimum number of operations, and the way that would work is basically in the first operation, the two smallest values would be this 1 and this 2, and if we apply that operation on the 1 and 2, we get 1 times 2 plus 2, and then we get 4, 11, 10, and 3, right? Notice how we're decreasing by one element in each iteration, or in each operation, because we're removing 2 and we're adding 1 back. Now, in the next operation, in the second one more specifically, we take the next smallest element, which would be this 3 and that resulting 4, and then we'd multiply them, and then add 4, we'd get 3 times 2 plus 4, which would then be 10. Now notice how that resulting array of only 3 after the first two operations would be 10, 11, and 10. In this case, all of the elements in that input are actually greater than or equal to 10, and so we only need a minimum of 2 operations to really just actually get the desired value. In example 2, we see that our input array nums is 1, 1, 2, 4, 9, and k is 20. In this case, we need a lot more operations, in this case, 4 operations, to actually get all of the values in our input array nums to be greater than or equal to 20. After one operation, the smallest two elements would be 1, 1. We actually multiply those together and then add that. We get 2. So then we have 2, 4, 9, 3. Then we actually have one more operation. The next two smallest elements would actually be that 2 and that 3. After applying that, we'd have 7, 4, and 9. Then after the third operation, the smallest two elements in that iteration would be 4 and 7. After applying the operation on those two smallest elements, we'd get 15, 9. And after the fourth operation, which we'd be working with 15 and 9, notice how after the third operation, we only have two elements, and so we have to actually apply the operation on those two specific elements. At least we have to have two elements in the input array nums to actually apply the operation. And applying the calculation or operation on 15 and 9, we get 33 as our result. And 33 is indeed greater than or equal to 20, which is the value of k, and so we can stop after 4 operations. That is actually the minimum number of operations, so that all of the elements or the single element in the input array are actually greater than or equal to 20. And the very important observation to make is that in every operation or in any iteration, the number of elements in our input array decreases by 1 because we're removing 2 elements and adding only 1 back. So for the constraints here, we see that the length of our input array nums is actually going to be at least 2, which is good. So that means we can apply at least one operation to the input array, and it's going to be within 2 times 10 to the 5th power. We're also given that any value in our input array nums is not going to exceed 10 to the 9th power, and the k value is not going to exceed that value either. So what are some very important observations that we can really make in this problem? Well, in nature, this problem really is just a straightforward simulation problem, right? They tell us what to do, they tell us how the operation is defined, and they tell us when to stop, right? This really is exactly just simulating the operations and the kind of structure of this problem in our code, right? It's really just a simple simulation problem, right? And to kind of put that more into context, how can we actually simulate this very efficiently? Because of course, sorting the array in every single iteration to actually get the smallest two values at each operation would be very inefficient, and so we have to kind of think of something a lot more efficient. And that's exactly where our main data structure comes into play. We can actually utilize something called the min heap, also known as a priority queue. And a min heap is actually just perfect for this problem because the kind of operation and the way it works is exactly how this problem is actually structured. They actually go hand in hand together, right? And the way that a min heap works, basically, it actually lets us access very quickly in very quick time and remove the smallest elements in a given collection or list. In this case, it's going to be a list, and that's very important in the context of this problem. And to kind of write that in a comment here, the whole operation of a min heap, basically, it allows us to access and remove the smallest elements of a given collection, or really just a list. I'll just say a list in the context of this problem, which is great because in each iteration or in each operation, we want the smallest integers. And the way the min heap works is that the smallest integers are always going to be at the top of the min heap. They're kind of going to be like the root node of the min heap that we can access in quick time, right? That's why min heap is very important and very key to really solve this problem, right? So kind of getting into how this solution is actually going to work. First of all, we actually initialize the min heap, and actually the way we can do that is simply turn our input array nums originally into the min heap, right? Basically inserting all the elements of nums into that min heap, and that's going to basically efficiently retrieve all the smallest elements, which is exactly what we want in each operation, right? We want to take the two smallest integers and work with them in every operation. And the way we can actually do this after we actually get them or initialize the min heap is actually start to simulate or actually perform those operations. And the way we can actually check that is while our heap contains more than one element. That means while the min heap contains at least two elements to actually work with it, and the smallest element of that min heap is still less than k, that means we still have to go on and make more operations because we haven't actually satisfied the problem yet. The smallest integer that we have, kind of like the bottleneck of the data structure, it's still not greater than k. We want all the elements to be greater than or equal to k, right? And we know if the smaller element is greater than k, we know that all the elements that are larger than it will also have to be greater than k as well, right? So basically in each operation, we first extract the two smallest elements, just say x and y in the context of this problem, from that min heap in each iteration or operation, and then compute that new value. That would be the operation that they give us, that calculation of the minimum of xy times 2 plus the maximum of those two values, and then insert that new value back into the heap and increment the number of operations that we make in each iteration that we do this for. And of course, we actually stop that process when either all the elements in the heap are actually greater than or equal to k, or we only have 1 or 0 elements left, meaning we can't actually apply the operation. We don't have enough elements to really do so. So with that high-level rundown out of the way, let's go ahead and dive straight into the code here. So what I'm first going to do, like I just talked about before, is actually kind of get the min heap initialization, or actually turn that input array into a min heap. And a very neat way to do that in Python, using the heap data structure, or using the heap module, is simply called the heap q module. So heap q dot, and the keyword I'm going to use in the context of this problem is going to be heapify. And what heapify does, it basically kind of converts a given list or data structure into a min heap by default, right? We're going to basically initialize the min heap with all the elements from nums, right? So for our parameter, of course, we're going to pass in the input array nums and actually initialize our operations. What our operations does, as you may imagine, basically it stores the number of operations that we actually perform on the input array while we actually haven't met the problem's conditions yet. Okay? And what we're really doing here, again, we're just turning it into a min heap, right? That's actually going to transform that list into a heap in place in linear time, and that is going to be very important for the context of this problem because, again, we want to efficiently retrieve the smallest elements of the input array in each operation, right? So now let's actually begin the while loop. Now let's actually begin the main loop while we haven't met our condition, or while we don't have any elements remaining. Basically, while the length of that nums, that min heap, now that we've heapified it, while that's greater than 1, meaning we at least have two elements, so we can actually still apply the operations to our input array, and we also want to make sure that nums at index 0, if that's still less than k, that means we haven't met the criterion yet. That means that we haven't actually had all the elements in our input array be greater than or equal to k. And the reason why we're checking nums at index 0 is because that's going to be the top of the min heap, basically the smallest element. And we know if the smallest element is greater than k, all the elements that are larger than it have to also be greater than or equal to k. And if the smallest element isn't greater than k, that's a bottleneck. We don't even care to check for the other ones. As long as this is the case, we still have to apply operations because we haven't actually satisfied the problem's constraints just yet. And now, in each iteration or in each operation of this while loop, we want to actually extract the two smallest elements. And a very simple way to do that in Python is basically get x to be heap q.heap_pop, and y, the second smallest element, to be heap q.heap_pop again. And the reason why we can safely just pop from the top of the min heap data structure is, of course, because we are actually guaranteed that the top of the input array is actually going to be the smallest value from the heap, right? Because that's exactly how a min heap is defined to be. The root node, or the topmost element that we pop from efficiently, is always going to have the smallest element in that given collection. And once we actually kind of pop off the two smallest elements, x and y, basically apply that pop operation for the smallest element 2 times, now we can actually get our x and y two smallest elements and work with them to begin that operation to compute the new value and insert the new value back into the heap. So basically, we literally have to simulate that calculation that they gave us. They gave us that every time we get the smallest elements, we want to literally just apply this. So it's basically as simple as copy and pasting this operation into the code here with the two kind of popped out smallest elements, x and y. So I'm literally just going to call it new value. That's the value that we're going to add up back into the input array, rather into the min heap. And it's going to be literally just applying that operation that the problem gave us, the minimum of the two smallest values in this iteration, x and y, multiplied by 2, plus the maximum of those two smallest elements, x and y, right? Exactly. We're literally calculating that new value to actually be inserted back into that min heap queue using the given formula. And that always makes sure that that new value is always going to be a combination of those two smallest elements, x and y, with the smaller one effectively just being doubled, right? And here again, to kind of reiterate, we're simply retrieving in efficient time the two most smallest elements. Okay, now let's actually, once we've actually computed the new value using the given calculation, now let's actually insert that new value back into the heap like the problem tells us to do so, right? So now that we've actually got that, we want to then use the heap push keyword here in Python for the heap queue library or module, and we're going to have two parameters. The first parameter is actually going to be the data structure that we want to push the new value onto, and the second parameter is going to be the value that we want to push onto. And in this case, the value that we want to push onto the input array nums, the min heap nums, is going to be the new value that we just computed on line 9 in each iteration or in each operation that we get or that we retrieve the two smallest elements. We're simply adding that new value of the current two smallest elements onto the heap while actually maintaining that heap property of having the minimum heap or the minimum value on the top of the data structure. Now, once we've actually done this, we just applied an operation, right? We just made an operation, didn't we? So we have to actually increment the number of operations we made in this iteration because, of course, we just made another operation. And very simply, we simply increment the number of operations that we made plus equals 1, right? We've actually used one more operation that we've actually performed, and so we increase its value accordingly. And effectively, once this while loop is actually done terminating, we simply return the number of operations that we did while we had enough elements to apply operations, and while the smallest element, the bottleneck element, still wasn't greater than k, meaning we still hadn't met the solution. But while this was true, while we actually applied operations, once it was done, once we actually did meet the problem's criteria, and once it stopped executing, once it terminated, we simply returned the number of operations that we actually performed on the input array as a whole, right? So if I were to submit this, this would actually be submitted, and this would actually be an accepted solution. Okay, let's see what I did wrong here. Probably just a very simple, yeah, okay. So as you can see, I actually completely forgot to pass in the parameter. I can't just pop from nothing. I have to actually heap pop the top element from the input array nums. Sorry about that. Now there should be an accepted solution. Now there should be valid. Let's go ahead and double check if it really works. And as you can see, this really is just about as efficient as you can get it to be. So to kind of reiterate how this code actually works as a whole, basically, we're systematically increasing the smallest elements in the array by, at each iteration or at each combination, we're combining the two most smallest elements until all the elements meet or exceed that threshold of k. And by actually always combining the two smallest elements at each operation, we're always making sure that the growth of that smallest value is always going to be as rapid as possible. That actually minimizes the number of operations that we actually require in the min heap property. Right, so for the runtime complexity, this is actually going to be a big O of n log n complexity, where n is going to be the length of our input array nums. Why? Because the actual primary operations within this main while loop here, that's actually going to be heap extractions and heap insertions like we saw with x and y and the new value, right? And in this case, each of those operations does actually have a logarithmic complexity relative to the number of elements in that heap. And so in the worst case, we might actually perform an operation for basically almost every single element in the array, and that would be a total time complexity, a big O, of n times that logarithmic log n complexity. So for the memory or space complexity, the space complexity is really just linear. It really just is a big O of n solution because, of course, at the end of the day, we are using that extra data structure heap queue. We are storing all the elements from an input array nums in the heap. So fully simplified, it's a linear or big O of n time complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.